Okay, in this section we're going to be solving trigonometric equations. So a trig equation is going to be, of course, an equation that has the variable inside of one of the trig function inputs. So an example of a very simple looking trigonometric equation, sine of x equals 1/2. So of course it's an equation because there's an equal sign and we're solving for the variable, and it's a trig equation because the variable is inside the input for the trig function. So we probably know by looking at this, based on what we've been doing the past few weeks here, that one solution to this is x equals pi over 6, because sine of pi over 6 equals 1/2, right? Sine of x equals 1/2. You're asking yourself, sine of what equals 1/2? And then you know that one answer is pi over 6 because that is a reference angle. So reference angles are going to be, they should be the first answer that pops into your head for most of these equations. So the issue with this is that that is not the only solution here. So here's the graph of sine. And when we're trying to solve sine of x equals 1/2, we're asking ourselves, what are the input values of sine that give us out this y value of 1/2? What are the x values that give us out this height y value of 1/2? So the one that we just found is actually this one right here, right? We just found this answer, which was pi over 6, but there's actually an infinite amount of other answers. We have all of these other points of intersection, and technically, since sine is periodic from negative infinity to infinity, it's going to intersect that horizontal 1/2 dotted line is going to intersect the sine curve at an infinite number of points. So that means there's actually an infinite number of solutions. So the first step for this is something we actually already did when we're answering these questions. How do we figure out an infinite number of solutions? Well, the first step we already did is we figure out what is the answer that it's a reference angle. So we just figured out that pi over 6 is one of our answers. And the next thing we're going to have to do here is use the periodic nature of sine to figure out the other answers. So we know that sine has a period of 2 pi, right? That little shape from 0 to 2 pi is going to repeat itself over and over and over again. This little shape right here for sine repeats itself over and over and over again. So the only thing we actually have to do for this is find the answers between 0 and 2 pi, which looks like there's only 2 of them. So we already found one of them is pi over 6. And then we also need to find this one right here. So on the next page, I'll talk about how I know this, but this answer is going to be 5 pi over 6. So even though there's an infinite number of solutions, we just figured out the 2 solutions between 0 and 2 pi. And then all we have to do is use the fact that these values are going to repeat themselves every 2 pi radians, since sine's period is 2 pi. So the answers for this equation, sine of x equals 1/2, we said one answer, x equals pi over 6. The other answer, x equals 5 pi over 6. And in order to write this in a way where it just repeats that value, essentially we need to figure out a way to add and subtract 2 pi to each of these answers an infinite number of times. So the way that we're going to do that is we're going to say plus 2 pi times n, where n is an integer. So n represents any positive or negative whole number. And these would be this is how we would write all of the solutions to this equation. Sine of x equals 1/2. All solutions are x equals pi over 6 plus 2 pi n. X equals 5 pi over 6 plus 2 pi n, where n is any integer. So what that means, for example, like what is this answer right over here? So let's say we wanted to figure out this value right here, which we don't really have to do, but if we really wanted to figure out what that value is, that's going to be pi over 6 plus 1 period, so plus 2 pi. So that's going to be using this part right here, pi over 6 plus 2 pi times 1. And then you can combine that, get common denominators, combine that if you want. I'm not going to. But long story short, what this little plus 2 pi n means is you can plug in any value for n, as long as it's an integer, a positive or negative whole number, and then simplify the expression, and then that'll give you another answer to this equation. Right, so just like what we saw for that example, this page is going to look a little bit lengthy. Just bear with me. I have everything typed up here. So like we just saw on the previous page, we just found all solutions to that equation, right? Anytime we're finding all solutions, that's when we're going to have that little plus 2n pi or 2 pi n. It doesn't matter how you write it. Typically, you're going to see it written as 2n pi. I'll write it as 2 pi n as well. It means the same thing. So finding all solutions, we're going to find the answers between 0 and 2 pi. And then for sine and cosine, we're going to put plus 2n pi. And then for tangent, we're going to do plus n pi. So the reason why it's different for sine and cosine compared with tangent, sine and cosine have a period of 2 pi. Tangent only has a period of pi. So finding all solutions, we're always going to have that at the end of the answers. The other way we can do this is finding the answers only over a given interval. The good thing is for that is it's almost always going to be over the interval 0 to 2 pi. So if we are only finding the answers over a given interval, which is 0 to 2 pi more often than not, then we find the answers, we circle them, and then we're done. We don't need to add plus 2 pi n plus n pi or whatever to the end. Just find the answers and you're done. So if this previous question just said find the answers from 0 to 2 pi, then we would just circle pi over 6 and 5 pi over 6, and then that would be it. And then we would be completely finished. Okay, so those are the two types of questions that we have to look out for when we're solving these. The good thing is they're almost the same. You just have to take into consideration that little last part for all solutions. And like we saw on the previous page, when we're solving these equations, we need to be able to know that reference angle table, which we learned several weeks ago, because one of the first steps to solving is going to be actually figuring out what the reference angle answer will be. So something I highly recommend doing here is also drawing out a graph for each one of these equations. And I'm going to write kind of the generic steps for how to solve these in a second here. But the graphs that I recommend drawing are just going to be these ones right here. Thankfully, we're only going to be solving equations involving sine, cosine, and tangent. We're not going to be doing them involving cosecant, secant, or cotangent. So basically, every single question that we do, every single equation that we're solving, should at least have one of these drawn. All of these are from 0 to 2 pi. So notice all of the x values are exactly the same. From 0 to 2 pi, same exact x values. We know sine looks like this, cosine looks like this, and then tangent, it's a little bit annoying, but tangent looks like this between 0 and 2 pi. So before we mention like the steps and the types of questions we're going to see, let's go back to that example on the first page. We were talking about the answer pi over 6. We said we knew that this was pi over 6 because that was a reference angle, right? So the question was, how do we figure out the angles, the answers that are not reference angles? So this is where it gets a little bit tricky. I have this more formally written on the next page. But usually when we talk about quadrants, we talk about quadrants like this, right? Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. When we're doing these types of questions, the quadrants that we're used to saying quadrants for are actually now these quadrant columns. So for example, quadrant 1, usually when we think about quadrant 1 up here, quadrant 1 is between 0 and 90 degrees or 0 and pi over 2 radians. Now, when we're dealing with trig functions, between 0 and pi over 2, that's actually going to be this little sliver right here. So quadrant 1, when I say quadrant 1, I'll try to remember to say quadrant 1 column, but I'm actually referring to this column between 0 and pi over 2 on the x-axis. Quadrant 2 is between 0 and pi. Quadrant 3 is between pi and 3 pi over 2. And quadrant 4 is between 3 pi over 2 and 2 pi. So once again, think of this as quadrant 1, quadrant 2, quadrant 3, quadrant 4, as these little columns between these normal x values that we see. So in quadrant 1, you can see that pi over 6 is in quadrant 1 because these are reference angles in quadrant 1. In quadrant 2, we said the answer that we found was 5 pi over 6. So the question is, how do we know how to find that in quadrant 2? I have this written on the next page, so I'm not going to write it here. But when we're in quadrant 2, I'll write it a little bit. It's going to be pi minus the reference angle. So I'm just going to use R for reference angle. Quadrant 1, the answer is a reference angle. Quadrant 2 is pi minus the reference angle. When you're in quadrant 3, it's pi plus the reference angle. Quadrant 4 is 2 pi minus the reference angle. So we didn't have any answers in quadrant 3 or 4 here, so we didn't have to worry about pi plus or 2 pi minus. We just had to do pi minus the reference angle for the answer in quadrant 2. So the reason that we do pi minus, pi plus, 2 pi minus just has to do with the symmetry for how far away it is from pi, essentially, and away from 2 pi in quadrant 2, 3, and 4. Okay, so like I said, I do have this all written down right here. If the answer is in quadrant 1, the answer is a reference angle. Quadrant 2, pi minus the reference angle. Quadrant 3, pi plus the reference angle. Quadrant 4, 2 pi minus the reference angle. I highly just recommend memorizing that just because it's going to make this a lot easier. Draw the picture, figure out what quadrant it's in, and apply those little mini formulas. Okay, so before I write down these generic steps over here, I'll write down the steps for solving this on the right. There's going to be 3 main types of questions that we're going to be solving, 3 types of equations. The first one is going to be the equations involving a single trig function. So these are going to be the easiest. These are the ones we're going to start with in a second. The second type is going to be the ones that are in quadratic form. We're going to have to solve these by factoring and using the zero product property. So just like we factor a quadratic. And then there's going to be using factoring to separate trig functions. Obviously, we're going to have to use factoring for this. Usually that's going to be GCF factoring, and then we use the zero product property. So for these generic steps, I'll try not to write like too much here. I'll try to keep it nice and short. Step 1 is going to be isolate or solve for the trig function. So solve for the trig function first. The way that we do that depends on what type of question we have over here on the left. Step 2, I'll say draw a graph. So we're going to draw a graph just like I wrote up here above, one of these 3, depending on if we're working with sine, cosine, or tangent. Step 3, I'll say we're going to determine the answers based on which quadrant the answers lie in. That's going to be using these little techniques, these little formulas up here. And then for step 4, once we have the answers, if we're finding it over the interval, we're done. We just circle them. If you're finding all solutions, you need to either add plus 2 pi n or plus n pi to your final answers. All right, so remember these little steps here. That's pretty much going to be the steps for all of these. Step 1 is going to be the one that can change a little bit different based on what the original question looks like. So let's start off with the easiest type, equations involving a single trig function. The step for this one to how we actually solve for the trig function, we're just going to isolate the function. And that's usually just going to be with combining like terms, using addition, subtraction. We're going to get all of the function terms on one side, constants on the other side. So first one, Find all solutions. 2 sine of x equals radical 3. So to solve this for sine, all we have to do is divide both sides by 2, right? So we end up getting sine of x equals divide both sides by 2. We get radical 3 over 2. So the next step now, we already have the trig function solved for. The next step, which a lot of people do not do this, even though I always say I recommend it, highly recommend it, is draw a picture. So draw a picture of sine, because this is for sine, obviously. Draw a picture from 0 to 2 pi. You don't even have to label these values. I'm just going to label it for this first one. If you don't want to label it, you don't have to label these, but you do need to mark them with their dashes. So 0, pi over 2 pi, 3 pi over 2, 2 pi. You don't need to label it, but you do need to have the dashes labeled, and the sign needs to be at least somewhat accurate. It doesn't have to be perfect. So that's sine. Now we're going to ask ourselves, when does sine equal radical 3 over 2? So go to radical 3 over 2 on the y-axis, put a horizontal line, and see how many times it intersects the graph. So it looks like it intersects it twice, right? We have 2 points of intersection. That means we have 2 main answers here. So next we go you don't even have to do this technically. I think it looks better if you do. Go vertical to the x-axis. Whatever those little X marks the spots are, those are the answers to our question. So the question is, what the heck are these answers? So for this first one on the left, this one is in quadrant 1, right? Remember quadrant 1, I'm referring to this quadrant slice between 0 and pi over 2. Since this is in quadrant 1, the answer is a reference angle. So we know that sine of pi over 3 equals radical 3 over 2. So we know that this value is pi over 3. So all of the other answers, in this case just one, comes down to knowing the reference angle. Because now for this next one is in quadrant 2. Since this answer is in quadrant 2, right away, you know it's going to be pi minus. So it's pi minus because it's in quadrant 2, and it's pi minus the reference angle. Pi minus pi over 3. Get common denominators, 3 pi over 3 minus pi over 3. That's 2 pi over 3. So we're basically done. When we're writing the answers here, we have x equals pi over 3, x equals 2 pi over 3. Then we just need to make sure we're answering the correct question. This says find all solutions. Since it doesn't just say find the solutions over the interval, we're finding all solutions. Since this is sine, we know the period of sine is 2 pi. That means we need to add plus 2 pi n to the end of both of these. And you should just write where n is an integer somewhere, just, for good, just to label what the heck n actually represents. So we have 2 main answers. Technically, we have an infinite amount of answers. We have pi over 3 and 2 pi over 3, but those are going to repeat every 2 pi radians. Right, so most of these questions look something like this. You first solve for the trig function, then you draw a graph, figure out what quadrants your answers are in, and then figure out, is it all solutions or just over the interval? So let's see another one. Find all solutions. 4 cosine of x equals 6 cosine of x plus radical 2. So right away, you probably notice that there's 2 separate cosine terms, right? So even though there's 2 separate cosine terms, this is still a single trig function because they're both just cosine. So just like a linear equation, let's get all of the cosines on one side, constants on the other side. So I'm going to go ahead. You don't even have to show this step if you don't want to. I'm going to get all of the cosines on the left. So 4 minus 6 gives us negative 2 cosine x equals radical 2. And then we're going to divide both sides to isolate cosine. Divide both sides by negative 2. So cosine of x equals radical 2 over negative 2. Or you can and should just write that as negative radical 2 over 2. So step 1 is done. We have cosine solved for. Cosine equals a number. Now step 2, graph cosine from 0 to 2 pi. And we always start these the same way because we're always using these same values. And then we know cosine looks something like this. So even though it doesn't have to be perfect, just make sure you have your points of intersection and your max and min points in those correct spots. So there's cosine. We want to know, when does this equal negative radical 2 over 2? Negative radical 2 over 2 is just somewhere between 0 and negative 1. Doesn't have to be perfect, just somewhere between 0 and negative 1. So we put a horizontal line straight across, and it looks like we have two answers. 2 points of intersection, we go vertical to the x-axis. So whatever those x marks the spots are, those are the two main answers for this equation. So the tricky part for this one, this is kind of as tricky as these can get once you get here, is a lot of the time, maybe more than half the time, a little bit more than half, is you're going to have an answer in quadrant 1, but there's no answer in quadrant 1 because the value is negative radical 2 over 2. We know all values in quadrant 1 are positive, so that's why there's no answer in quadrant 1. So we actually have an answer in quadrant 2 and in quadrant 3, right? So right away, as soon as you see the answer in quadrant 2, you're probably thinking pi minus. And as soon as you see the answer in quadrant 3, you're thinking pi plus. So pi minus in quadrant 2, pi plus in quadrant 3. The last little thing we have to worry about is what the heck are we actually adding and subtracting from pi? This is when we have to kind of use our techniques that we used with the inverse trig stuff. Anytime this is a negative value, we're going to pretend it is positive. So we want to pretend that we're solving cosine of what reference angle equals radical 2 over 2, because we need the reference angle. So we know that cosine of pi over 4 is radical 2 over 2. So this reference angle is the angle that we're actually using to add and subtract from pi. So once again, anytime it equals a negative value, you're not going to have a reference angle answer. You need the reference angle to figure out the other answers. So you pretend that it's positive just so you can use this reference angle. And this is the value that we're adding and subtracting. So pi minus pi over 4 gives us 3 pi over 4. And then pi plus pi over 4 gives us 5 pi over 4. So get common denominators. These are our two main answers. I'll write them over here on the left. We have 3 pi over 4 and 5 pi over 4. Once again, find all solutions. This is for cosine. Cosine has a period of 2 pi. So we're going to do plus 2 pi n to the end where n is, I'm just going to abbreviate, n is an integer. All right, so pretty similar like how we did it. These are all going to be really similar. The answers we get are just going to be, different for most of these. All right, so once again, all we did here was isolate cosine, draw the graph of cosine, figure out what quadrant the answers are in. This time we had to sneakily get the reference angle first, get the answers doing pi minus, pi plus. All solutions, we had to do plus 2 pi n to the answers. So this next one is really similar to the one we just did. I'll leave it for you guys to test, try out, maybe go take a look in the notes. Let's move on to, let's take a look at this next one where it's maybe a little bit trickier. So next we're going to solve the equation on the interval 0 to 2 pi. So two things for this. First, notice that we don't need plus 2 pi n or anything because we're only solving it on the interval. Notice that we're also solving this on our normal interval, 0 to 2 pi. But also notice we're not including 2 pi as an answer. So if we end up getting 2 pi as an answer, since there's a parenthesis, we actually would not include it because it's saying do not include 2 pi if it is actually an answer. So this one looks a lot different. Sine of x minus 1 times 2 cosine of x minus 1 equals 0. So two things to notice, maybe more than two. Notice that we have two trig functions, right? Sine and cosine, two separate ones. Also notice this is already factored, right? Something times something, this is already factored. And then also notice it's equal to 0. Anytime you have something factored equal to 0 and you're solving the equation, you can use the zero product property, which means you're going to set this up and set both of these factors equal to 0 separately and solve them separately. So just like we did when we were solving polynomial equations, we do the same thing. You're going to take both of these factors and set them equal to 0 separately and solve these equations separately, because the only way something times something equals 0 is if at least one of those things is in fact 0. So let's take a look at the one on the left. Sine of x minus 1 equals 0. All we have to do is solve this for sine by adding 1 to both sides. So let's just go ahead and do this, finish this one off. Sine of x equals 1. Anytime you have sine or cosine equal -1, 0, or 1, you might be able to do it in your head. I'm just going to draw it out though, just so we have it drawn in front of us. Okay, so here is the graph of sine over here on the left. Notice I didn't even label anything, but the reason I said you might be able to do it in your head is because we want to see when does it equal 1. It equals 1 at that maximum value. So we ask ourselves, what is that dash right there? That first dash is pi over 2, and then that's just our answer. So we only had one answer for this one, which is x equals pi over 2. So I'll come back to that. I'll circle the answer all together when we're completely done. So we're already done with the one on the left. The one on the right, 2 cosine of x minus 1 equals 0. We need to solve this for cosine by first adding 1 to both sides and then dividing both sides by 2. So we end up getting cosine of x equals 1/2. Notice that all of these trig functions, sine of x equals 1, cosine of x equals 1/2, those values are going to be values that we see on the reference angle table, right? 0, 1/2, radical 2 over 2, radical 3 over 2, and 1. We're going to see those a lot for sine and cosine. So we can go ahead and graph cosine on the right. So here's the graph of cosine. I didn't even bother labeling anything. We want to know when does it equal positive 1/2. Horizontal line across. It looks like we have 2 points of intersection. One of them is in quadrant 1, as expected because it's positive, so we're going to have a reference angle answer. The other one is in quadrant 4. So quadrant 1, 2, 3, 4. We have quadrant 1 and quadrant 4 as our answers. So we just need to ask ourselves for this always do the reference angle one first. We want to ask ourselves sine of what reference angle equals 1/2. That's going to be pi over 3. So once again, we know that cosine of pi over 3, the reference angle pi over 3, is 1/2. So pi over 3 is one of the answers. And then the other answer over here in quadrant 4, as soon as we know it's in quadrant 4, you can just automatically write down 2 pi minus. So 2 pi minus pi over 3, that's 6 pi over 3 minus pi over 3 after we get common denominators, and we get 5 pi over 3. So we end up getting 2 answers for this equation on the right. You can write these all in one. I guess I'll do that because it'll look a little bit nicer. We have 3 answers. From the one on the left, we had pi over 2. The one on the right, pi over 3, 5 pi over 3. And this one, we only were solving them over the interval, so we don't need to add the 2 pi n at the end. Right, so that's the first type of question where we isolate one trig function and just get it as like sine of x equals 1, cosine of x equals 1/2, draw the graph, and figure out the answers based on what quadrant it's in. This one is a little bit trickier because it was factored. We had to use the zero product property, and we had to solve 2 separate equations, essentially. So next, this is probably going to be one of the trickiest ones, but only because of factoring. If you have a trig equation in quadratic form, technically we can do this, we might be able to do it a few different ways, but we can, long story short, is we can solve this using our same methods for how we solve quadratic equations. So you're probably saying to yourself, if we have trig functions, how the heck is it in quadratic form? Because obviously trig expressions are not quadratic expressions, right? Trig expressions are not polynomial expressions. So we say something's in quadratic form if it's in this form au squared plus bu plus c, where it's not an x, it's not ax squared plus bx plus c, but the u can be anything else. So in this case, the u is going to be a trig function. So for example, we have this trig equation, 2 cosine squared x plus cosine x minus 1 equals 0. So your main goal, always remember kind of your main first goal, is to get the trig function solved for. It needs to be the trig function equals a number, and then you draw the graph and go from there. This one, you do have one trig function of just cosine, but you have a cosine squared and just a normal cosine to the first power. So you can't just solve this using the same methods that we just did because of the cosine squared. So technically speaking, we might be able to use factoring. We could always use the quadratic formula, which maybe I'll mention after. And we might be able to use the square root property. So if you wanted to try to factor this, I'll leave it for you guys to go back and test. But if you wanted to factor this on the side, I recommend writing it instead of cosine of x, just rewrite it as x. So instead of 2 cosine squared plus cosine minus 1, write it as 2x squared plus x minus 1. And this actually factors. So if you ended up factoring this, you would get 2x minus 1 times x plus 1. So this is factoring a quadratic when the leading term's coefficient is not a 1. It's a little bit harder, but hopefully you remember how to do that. If not, you might have to go back and review it. So instead of an x, we have a cosine. So this is just going to factor to 2 cosine of x minus 1 times cosine of x plus 1 all equals 0. And now we can do this the same way that we just did the previous one. So basically, as soon as you see one that's in quadratic form, where you have a squared and then just an exponent of 1, in my opinion, factoring is the quickest way to do it. But if you forgot how to factor, you would have to use the quadratic formula, which I'll mention after. So now that it's factored, something times something equals 0, we're going to use the zero product property and set both of these factors equal to 0 separately. So 2 cosine x minus 1 equals 0, and cosine x plus 1 equals 0. And let's solve the one on the left first. So we need to solve for cosine. So we need to add 1 to both sides and then divide both sides by 2. So we end up getting cosine of x equals 1/2. So let's go ahead and draw the graph of cosine. So here's the graph of cosine from 0 to 2 pi. We want to know, when does it equal 1/2 horizontal dashed line, circle where it intersects, straight line down, and we have an answer in quadrant. I didn't do that perfectly, but either way, that's going to be quadrant 1 and quadrant 4. So even though the graphs don't have to be perfect when you draw them, they do have to be good enough so you know when you do a vertical line what quadrant column the answer's in. So when we have the answer here in quadrant 1, since it's in quadrant 1, we know it's a reference angle. When does cosine equal 1/2 as a reference angle? That's going to be pi over 3. So we know that cosine of pi over 3 is 1/2. So we already know pi over 3 is one of the answers. So next, we have this one over here. Since this is in quadrant 4, it's 2 pi minus the reference angle. That's 6 pi over 3 minus pi over 3. That gives us 5 pi over 3. So we already have the two answers on the left. Let's take a look at the one on the right. Cosine of x plus 1 equals 0. Subtract 1 on both sides. Cosine of x equals -1. So this is actually still cosine. So we just need to ask ourselves, when does cosine equal -1? So -1 is right here, horizontal line, hits it at this minimum point. That's going to be this value right here, which is a value of pi, because that's on the dashed line. So always remember, even though it doesn't have to be perfect for the graph, you should have the points of intersection correct on the dashes, as well as the max and min correct. And then we're actually done. We actually have all three of our answers, and we're only solving this over the interval, so we don't need to put plus 2 pi n. So our three answers are x equals pi over 3, x equals pi, and x equals 5 pi over 3. All right, so like I said, for this one, these can be a little tricky when they're in this quadratic form, when you have something squared. I do recommend trying to factor first. If you forgot how to factor, you could always use the quadratic formula when it's in quadratic form, when you have one of them that are squared. So usually the quadratic formula says x equals -b plus or minus the square root of b squared minus 4ac, all divided by 2a. So that quadratic formula is for a quadratic equation, ax squared plus bx plus c equals 0. Instead of an x, we have a cosine of x. So instead of x equals, it's cosine of x equals. So if you don't like factoring, you would have to use whatever your trig function is. Instead of x equals, it's cosine of x equals. But then you do it exactly the same way. So you would use a equals 2, b equals 1, c equals -1. You would plug all of these values in, a, b, and c, into your formula, and you would simplify all the way down. Once you simplify it all the way, thanks to the plus or minus that's in there, you would actually end up getting two things. You would get cosine of x equals 1/2, cosine of x equals -1. So from the quadratic formula, you would end up reaching this same step down here, and then you could figure out, when does cosine equal 1/2 and -1 using the graph like we just did. So if you like the quadratic formula, try to do it that way. I recommend trying to factor it instead, though. Okay, let's see another one of these quadratic forms. So 4 sine squared x minus 1 equals 0. We want to solve this on the interval 0 to 2 pi once again. So this is still in quadratic form because we have something squared, right? So you could use the quadratic formula if you really wanted to, but just like for the quadratic equations, if there's no x term, then you can just use the square root property. So for example, if you were just solving 4x squared minus 1 equals 0, there's no x term. All you have to do is solve for x squared and then take the square root of both sides, hence the name the square root property. So for that, we would end up getting plus or minus the square root of 1/4, which is plus or minus 1/2. We're going to do the same thing here. We're going to solve for sine squared and then take the square root of both sides. So first, we're going to go ahead and add 1 to both sides. And then we're going to divide both sides by 4. And then we're going to square root both sides and get plus or minus the square root of 1/4, which is 1/2. So we end up getting sine of x equals plus or minus, so positive and negative 1/2. So notice that even though it looks a lot harder with the trig function in there, it's literally the same exact thing as we just did over here on the right. Okay, so since we have the trig function solved for, let's go ahead and draw the graph from 0 to 2 pi. So this is the graph of sine of x from 0 to 2 pi. And we want to know two things. We want to know, when does this equal positive and negative 1/2? So that means we not only have to do positive 1/2 up here, but we also have to do negative 1/2 down there. So this is going to be horizontal line for 1/2, horizontal line for negative 1/2, and see all of these points of intersection. It looks like we have 2 of them. So as you probably noticed by now, we do get 2 answers a lot for these. We have 2 of these answers in quadrant 1 and 2. And then we also have 2 more answers in quadrant 3 and 4. So at first, this probably seems kind of annoying because we have all of these answers everywhere. But remember, all we have to do is figure out what is the answer in quadrant 1, what is the reference angle answer in quadrant 1, and then in quadrant 2, we do pi minus, quadrant 3, pi plus, quadrant 4, 2 pi minus. So taking a look at this answer in quadrant 1, we know that sine equals 1/2 when it's sine of pi over 6, right? Sine of pi over 6 equals 1/2. So that means pi over 6 is this first answer in quadrant 1. And then, like I said also, since we have this answer here in quadrant 2, it's pi minus. This answer over here in quadrant 3 is pi plus. And then this one over here in quadrant 4 is 2 pi minus. So even though it looks annoying because we have all of these answers, if you just remember reference angle pi plus, pi minus, or sorry, reference angle pi minus, pi plus, 2 pi minus, hopefully it's not bad. And then of course the value that we're adding and subtracting to all of these is that reference angle itself every single time. So pi minus pi over 6 is 6 pi over 6 minus pi over 6, which is 5 pi over 6. Pi plus pi over 6, 6 pi over 6 plus pi over 6 is 7 pi over 6. And then 2 pi minus pi over 6 is 12 pi over 6 minus pi over 6, which is 11 pi over 6. So just make sure you don't mess up getting common denominators for these fractions. And we have these 4 answers. So all we have to do is write them down, circle them because we're only finding these answers because we only cared about the answers over this interval. So that one, once again, might have been a little tricky for different reasons. We just had to solve for sine squared first and then square root both sides. And we just ended up getting an answer in every single quadrant. Right, so for the last couple, maybe 2 questions here. So it's kind of similar to what we just did with factoring 2 examples ago, except this factoring that I'm basically referring to for the most part for this little section here is going to be GCF factoring. So in order for factoring to help us, we need to get everything on the same side of the equation set equal to 0. Factor, use the zero product property, and then set all the factors equal to 0 and finish solving from there. So for this first one, solve on the interval 0 to 2 pi, sine of x plus 2 sine of x cosine of x equals 0. Notice how it's a little different just because we have 2 separate trig functions. We have sine and cosine. So we already have everything on the same side set equal to 0. The GCF between both of these terms looks like it's sine of x. So we're going to factor out a sine of x. Then we need to think about what's left over. Remember, whatever's left over is the original expression divided by the GCF. So sine divided by sine is 1. And then 2 sine, cosine divided by sine, we're just left with 2 cosine of x. So we have sine of x gets factored out front, sine times 1 plus 2 cosine equals 0. Now all we have to do here is use the zero product property. And we're going to take both of these factors separately, set them equal to 0, and solve from there. So don't forget, the only way you can use a zero product property and start setting different things equal to 0 is if those things are factors. You have to have something times something to use this property. So on the left, let's go ahead and draw sine on the left. It was already solved for. We already had sine of x equals 0. So we want to know, when does this equal 0? Well, it looks like it equals 0 at 0. It equals 0 at pi. And then technically it also equals 0 at 2 pi, But remember what we said before? Based on how this interval is written, we're not including 2 pi as an answer. So even though it does equal 0 at 2 pi, based on the interval that's given to us, we're not including it as the answer. The main reason I have it set up like this for the notes is because that's how a lot of the homework questions and stuff can be set up. So I just want to make sure we're careful right away. So this one was a little bit easier than some of the other ones because the answers are just x equals 0 and x equals pi. So for the one on the right, we need to go ahead and solve for cosine, subtract 1 on both sides, and then divide both sides by 2. So cosine of x equals -1/2. Let's go ahead and draw cosine. So here's my drawing of cosine, and we have when does it equal -1/2? Horizontal line straight across. So as usual, 2 points of intersection. It looks like we have quadrant 2 and quadrant 3. Before we even figure out what these answers are, since you know that one of them's in quadrant 2, you can just write pi minus right away. And then for the one in quadrant 3, you can put pi plus right away. Now the last little question that we have, before we have all of the answers here, is what value are we adding and subtracting? So remember that when we don't have a reference angle answer, that's because the initial value that it's set equal to is negative. We always have to pretend it's positive and then figure out the reference angle from there. So ignore the negative. When does cosine equal 1/2? That's going to be the reference angle of pi over 3. So pi over 3 is not an answer, but that's going to be the value that we're adding and subtracting. So pi minus pi over 3 is 2 pi over 3. And pi plus pi over 3 is 4 pi over 3. And those are the two answers for this equation on the right. So we have, looks like 4 separate answers. Since we're only solving this over the interval, we don't need plus 2 and pi. I'm going to write all of these answers in one big chunk again. X equals 0, pi, 2 pi over 3, and 4 pi over 3. Okay, so when in doubt, if you're completely confused by a question, chances are I bet it's a factoring question. Get everything on the same side set equal to 0 and try some sort of factoring technique and then the zero product property. So let's take a look at one more for this section. Solve on the interval 0 to 2 pi once again. Tangent of x times sine squared x equals 3 tangent of x. So right away, we see that we have two separate trig functions, right? We have tangent and sine. And the trick, so I'm going to write, do not do this, do not do. I see a lot of people say, oh, we have a tangent on both sides. Let's divide both sides by tangent and cancel off tangent and get sine squared equals 3. So you should never do that when you're solving any type of equation. Never divide both sides by the term with a variable and cancel it off. If you cancel off a variable in an equation with division, you're actually getting rid of an answer, at least one answer. So doing that, you're actually getting rid of you're getting it half wrong right away. So don't do that. You're going to use addition or subtraction. Let's go ahead and move. Let's get everything on the left side of the equation. So let's subtract that over. These are not like terms, so you can't combine them. So it's tangent times sine squared minus 3 tan x. That cancels on the right, so we're left with 0 on the right. So get everything on the same side using addition or subtraction, set equal to 0. And now let's try factoring. So there is a GCF between these two terms. It looks like the GCF is tangent, right? So factor out a tangent. We're going to be left with sine squared x minus 3 equals 0. So now that we have everything factored, set equal to 0, zero product property, make that little T chart thingy, set tangent equal to 0. Set sine squared x minus 3 equal to 0. And since the one on the left is our tangent's already solved for, let's go ahead and graph tangent. I'll actually show this one because we haven't had to graph it yet. So we're still using the same values. We have 0, pi over 2, pi, 3 pi over 2, and 2 pi. And remember, three things with tangent. It has vertical asymptotes when cosine equals 0. So that's at all the integer pi over 2's. And then it's going to equal 0 when sine equals 0, which are the integer multiples of pi. And then the third thing you have to remember is that it's always increasing. So that's going to be increasing, 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 and that's the graph of tangent from 0 to 2 pi. So we need to ask ourselves, when does it equal 0? So when is it on the x-axis? That's going to be right here at 0, right here at pi. Technically, it does equal 0 at 2 pi, but remember, we're just not including 2 pi based on how this question is worded. So we're not including 2 pi as an answer. So we only have two answers from this, x equals 0 and x equals pi. So not as bad as it might have seemed from the beginning. Let's take a look at the one on the right, sine squared x minus 3 equals 0. So this is a squared, so we're still just going to start by solving for sine squared. We're going to add 3 to both sides, and then we're going to square root both sides. So sine of x equals plus or minus the square root of 3. So usually when we get to this point, we want to draw the graph and see when it equals radical 3 and negative radical 3. It might not seem like there's anything wrong with this, but sine, that radical 3 is not one of those typical values that we see in our reference angle table. So in fact, radical 3 is outside the range of sine. We know that the range of sine is negative 1 to 1 because radical 3 is greater than 1, negative radical 3 is less than 1. So sine of x will never get up to radical 3 or get down to negative radical 3. So if you recognize that right away, you can save yourself a lot of time and frustration of not understanding how to figure that out. There's actually no solutions for that one. So all we actually have, we're actually done. We only have these two answers. I'm just going to write them down here so it looks a little bit cleaner. We have x equals 0 and x equals pi for this entire last equation. Right, so clearly you just need to make sure that you're comfortable with that little reference angle table, be able to think backwards in terms of the reference angles. We did stuff with isolating the trig function first, solving these from quadratic form, and using factoring, GCF factoring, to solve these as well. All right, so that is it for this section.